Now we can start the party. Good morning. Happy Wednesday. Oh boy. So nice to have you here. Right down here, I've got some piles going for problem set 6, take home quiz 6, and the final exam prep. If you could turn those in, that would be great. Also, I think I've returned everybody the work from the exam and QA3, but if you don't, there's a pile going up here. We have an extra credit presentation this morning. Yana and Elle are going to talk about mushrooms. Take it away.
All right. Good? Okay.
Sweet.
All right. So the first question I'm going to ask you guys is what you think the right way to pronounce fungi is. So who here thinks that it's fungi? Who thinks it's fungi? Okay. I agree with fungi because it sounds right with the fungus. So, fungus are a little bit like plants, and they're a lot more like animals than you might think. So today, scientists estimate that there are around 1.5 million species on Earth, though in a formal way we know only 100,000 of them. Sorry about that. I was running here and then I'm really anxious in front of people.
Yeah, nice to have you.
Right. So the 100,000 of them that we know are pretty wonderful, weird, and in some cases deadly. The fact is, death is what fungi is all about. So, fungi, like yeast, can be fun, and it can come in forms of beer, wine, bread, but fungi can also be found in diseases. So fungi can be found in athlete's foot and deadly like histoplasmosis is what I wrote. But basically fungi can even make people go crazy. And when fungus like Claviceps purpurea grows on grains used to make bread, it causes nervous spasms, burning sensations, hallucinations, and temporary insanity. The destruction that some fungi bring to other animals. Around more than 6 million bats in North America died due to fungal disease called white nose syndrome. Several extinctions of amphibians have also been found. Almost 1/3 of all amphibians. So the guy who found out that yeast decomposes into sugar was named Pasteur. And it turns out that most fungi spend most of their time decomposing all kinds of organic matter. Often matter is dead when fungi get to it, but not always. When a tree or a person or deer kneels over, fungi move in and start the process of decomposition. Same for spoiled fruits. The fungus that grows on it is the same thing. So if it weren't for this fungal function, plants and animals wouldn't exist because the elements that they take would never return. Thankfully, the decomposition performed by fungi recycles into the nutrients for the enjoyment of the plants and animals. So fungi are things called heterotrophs, but instead of eating, like humans do, they absorb the nutrition from their surroundings. So basically, they do most of the secreting of the powerful enzymes that break down complex molecules into smaller organic compounds, which they use to feed, grow, and reproduce. Most multicellular fungi contain networks of tiny filaments called hyphae that grow through and whatever they are feasting on. So unlike plant cells, which are made of cellulose, fungi are strengthened by a thing called chitin, which can be found in the exoskeletons of insects and spiders. So I'm going to talk about some of the parts of the mushroom. The cap is the little round top on the very top. The gills are the inside little parts that you can see peeking out, stripes. The stipe is just like the trunk of the mushroom, and the spores are the little dots on it. Okay, I'm gonna let you talk for a while.
Mushrooms are nutritious. They're a great substitute for meat for people who don't eat meat, like vegetarians, because they're high in protein. They have bioactive proteins, which is actually pretty cool because they're great for the immune system. They're great. They're antimicrobial and antibacterial agents. So they help keep you from getting sick. Fungi, they also have vitamin C, which is it's good for your skin. It helps strengthen the dermis and the epidermis and protects from UV rays. So it essentially helps protect you from skin cancer a little bit. Mushrooms are also great sources of minerals. A study by the National Health and Nutrition Examination Survey, it determined that eating a survey of edible mushrooms, adding it to your diet, it helps you get the minerals that people are typically lacking from their diets, maybe lacking from fruit or vegetables, but mushrooms are a great way to get them. It's one of the one of the best sources of sulfur antioxidants and other minerals that can be found in mushrooms are potassium, phosphorus, sodium, calcium. It's great for your immune system, really. It has anti-inflammatory agents, which can protect you from heart disease, arthritis, Alzheimer's, and the calcium in some mushrooms help with bone density.
That's good. And so, while some members of the fungus family are pretty dangerous, I'm going to talk more about the really cool ones. So up here I have a lot of pictures of some of the most dangerous types of mushrooms. So as you can see, most of them look like a normal mushroom. I'm not an expert in mushroom picking. I know some of my family used to go mushroom picking in Moldova, but I've never gone here. I have some relatives that have gone, but it's a very dangerous thing, so I wouldn't recommend going by yourself. You'd want to have an expert. Don't eat anything you don't know. Honestly, just be super, super careful about it. A picture that I was going to add on here was one of my favorite kinds of like instances of these very dangerous mushrooms, and it comes from the fact that some of them can infest themselves into the minds of ants and just completely take over their mind towards self-destruction. So it sounded very cool when I was reading about it. It's just like, it sounds like it's coming from a movie where something is just infesting someone's mind and just self-destruction. So what else do I know about this? That fungi, they just thrive on death. Basically, the decomposition of fungi can be found in so many different things. It can be found in the soil, like when you're gardening. If any of you have planted a garden, the fungi is all over the soil. It helps decompose all those plants into tiny little filaments that can reproduce. So through the process of death, the fungi also creates life. So another cool thing that I found about mushrooms is that Oregon is home to one of the largest species of mushrooms. And I have a fact about it. It says it's 2,386 acres of these mushrooms. They're called honey mushrooms, and they're found in eastern Oregon in the Blue Mountains in that area. And it's basically the largest organism on Earth. I mean, by area, it's pretty large. And then I found some fake pictures on Google of ginormous mushrooms. Those don't exist, that's just edited. But it was interesting to look for those. Basically, they're tiny, they're yellow. I think I've even seen them around these parts. Very cool picture to look up if you have time. And yeah, again, there's like around 4 parts of mushrooms: the decomposers, the mutualists, the predators, and the parasites. And there's so much to learn about them. So it's a very interesting topic to talk about.
Speaking of the largest fungus, it's the humongous fungus, as they named it. It is the largest living organism on the earth. There was another mushroom that was pretty close to that in Michigan, but the one in eastern Oregon in the Blue Mountains in the Malheur National Forest, that's the biggest one. by mass, the largest living organism by mass. Like Yana said, it's about 2,400 acres, which is about 3.7 square miles. It's a giant fungus. And the cool thing about it is most of it is underground in the root system of trees. It's not usually seen above ground. You might see it a little bit in the fall after it starts raining on trees that it's attached to. It might be at the base of the trees. And it's the honey mushroom that you can see, which is actually edible, but only if you cook it really well. Otherwise, it might give you some stomach aches. It's called the Armillaria ostoyae, which is a fun name. As Yana said earlier, mushrooms can be parasitic or infectious. Well, this is an example of kind of a parasitic mushroom. It infects trees, mostly grand firs. Those are the most common, most coniferous trees actually, which is why it's so big in Eastern Oregon. It will infect their root system and kind of go along the roots up into the tree. And then you can see mycelium. It's under the bark of infected trees. It's kind of white, and it's when the bark can easily peel off. You'll see it. That's one way to know a live tree is infected. It essentially eats the tree. It eats all the wood away. A long dead tree, you can tell it was infected if it loses branches or bark. Recently dead, the tree might have some red needles. And a living dead tree, like I said, it'll have the mycelium, and it might be like exuding resin from the base. Or have those mushrooms at the base of the tree. It's kind of cool. It grows about 0.7 to 3.3 feet per year, which is actually kind of a lot. I was really surprised. And this fungus, it's said to be about almost 9,000 years old. That's a really old fungus. It eats away at some of the old growth forests in Eastern Oregon. And it takes about 20 to 50 years for it to kill a tree, so it's a slow death for those trees. Wouldn't want that. It also weighs about 35,000 tons. That's the estimate of this fungus. It's hard to say because it's underground, and not many people want to research fungus in Eastern Oregon, but it's such a cool thing. Anyways, mushrooms are really cool. They're nutritious, also very deadly, and it's the largest living organism, and in Oregon. So thank you.
Any questions on mushrooms?
For like as much as the fungus is growing, is that in like all directions or just in is it going any particular way?
I think it's in all directions as long as it's going through a tree's root system. Like it's connected underground through root systems. Yeah.
Are they trying anything to like combat it, or are they just letting nature do its thing? Do you know?
I was trying to look into that, and I wasn't seeing much, but it looks like they were just letting nature run its course. It did say that what with more recent fire activity, it has kind of sped up its growth, probably because there are more downed trees, but I'm not entirely sure on that.
We watched a video in biology based on this exact thing, and I think they tried, but it would be way too hard.
Back in the 80s, they did a whole campaign of like digging out the root systems to take out the honey mushroom to see if we could like remove the mycelium from each tree. The problem is because it's growing up and under the tree barks, it's really hard to tell which tree is infected until you have actually almost killed the tree itself.
Yeah.
And it's very expensive because it's very effective, but it's very expensive.
Yeah, that makes complete sense to me. I mean, it starts in the roots and works its way up the tree, and by the time it's up the tree's already gone. There's no point of return there. All right.
Nice job. Well done. Excellent job. Last year.
we were going to Idaho, so.
It's in my
It's pretty shrubby yellow, and it's in the rain shadow. But
I like that part.
Yeah, no problem.
I like the desert.
No.
I mean, I grew up like half of my life with everything. My grandparents lived in Idaho, so I'm used to it. But I just found it way better. It's nice to visit, not to stay.
I've lived in the down.
Okay, so excellent presentation. So what we're going to do on our last 2 days of lecture, which is just crazy to say, but it's true. On the last 2 days of lecture, we're going to go over some review stuff, all right, for next week. Before we do that, just let you know that up here there's piles, and most of you turned the stuff in. Problem set 6, take-home quiz 6, final exam prep. And on the far side over there, I've got some work to return to you from the exam, the QA3 lab, stuff like that. It should be cool. But what I do want to talk about now, just never a dull moment, is what's going to happen next week. Woohoo! So next week, there's no labs, there's no lectures, stuff like that. What will happen is there's a lecture final and a lab final. And the lecture final will be in this room. It'll be next week, Wednesday, a week from today, from 8:45 to 10:45. 40 multiple choice questions, covers all the different chapters that we've studied. If you hear anything about an ACS final, ignore it, all right? The ACS final is something we did pre-COVID, and for some reason that continues to haunt my class as it goes through. It's just a regular final written by me, so it'll be similar in types of questions and stuff to what you've seen. When you come next Wednesday, bring your calculator, definitely. You're welcome to have a note sheet, single page, double-sided. It'll go about 2 hours and you'll be good. Now the lab final, what's going to happen on that is Monday morning, you're going to get a link to the lab final. You should print it out, complete it, and you'll turn that in your case, Wednesday, 8:45 a.m. before you take the lecture final. So you'll turn the lab final in Wednesday, 8:45, get the link Monday morning. Lecture final, 8:45 to 10:45. Gino's opens at 11. I mean, by 10:45 a.m. on Wednesday, he'll be done. Just say no, kids. Anyway, questions? Any of that? All right. So what I will do in the time I have left is we'll just kind of go through some sample questions. And final grades will be posted by Friday, blah, blah, blah. There's no way to relearn all the material that you've already seen this whole year, right? Because it's been a lot of stuff. So what I would do is just look over your past work, all right? And kind of familiarize yourself with the concepts. Maybe practice ones that are a little stickier to you. If you don't have some of your old work, and I understand that completely, you can look on the other websites I have. So like our website is mhchem.org/223 for Chem 223. There's also an mhchem.org/221 for Chem 221 and something for 222. And you can look over sample exams and quizzes, problem sets, my lectures and stuff, my video lectures, whatever you want. So try to refamiliarize yourself with it, but don't get worried if it's not 100% because it's a whole year's worth of material. But my goal in this section is just to remind you how much you have learned and how much is inside here, all right? Might be a little bit dusty, might have to dust it off a little bit to get it good to go, but it's up there, all right? If you have questions on anything, of course I'm here for you big time. We're just about to the end. Are there any questions at this moment? Okay. All right. So we'll just go through some questions, starting with Chem 221. We'll do a little bit of Chem 223, although I'll focus more on Chem 221 and Chem 222, just because those are the classes most of us haven't seen for a while. So let's go way back to the good old days, Chem 221, and this is a question about iron 58, all right? And the question is, which one of these has the right composition for an iron 58 atom? So see if you can figure out which of those would be the best answer, and we'll go from there. So the periodic table, greatest cheat sheet ever made. It's organized by those little blue numbers on these periodic tables, and those blue numbers are called the atomic numbers. Do the atomic numbers, what do they represent? Protons, that's right. So for this question, what I would do is start to look on the periodic table where iron is. Now, iron is Fe, the Latin phrase is blah, blah, blah. But what we're after here is that little blue number, 26. And 26 represents the number of protons. So iron 58 has 26 protons. Now, a neutral atom, all right, of iron will have equal protons and electrons. So if it has 26 protons, it's going to have 26 electrons to make it neutral. Remember, protons are positive, electrons are negative. And then finally, this is what they call the mass number. And mass number is useful when you're doing E equals mc squared kind of stuff, and other uses for it. But anyway, that number represents protons plus neutrons. So if you take this number 58 and you subtract the 26 protons, that'll tell you how many neutrons there are. And so if you got answer B, then well done. Most of the mass of an atom comes from the nucleus, which is where the protons and the neutrons are. And that's why this 58 represents the total protons plus neutrons. It takes roughly 2,000 electrons to make the mass of a proton. They're very, very small. But of course, electrons help keep things neutral, electrically, stuff like that. Any questions? Okay, here's a question. We have a nitrogen and oxygen compound. NXOY is the generic way to say it. And we find that with this compound, this particular one has a nitrogen mass percentage of 46.67%. So see if you can use this information to find the empirical formula of this compound. Remember, the compound formulas are always mole-based. So what I would do is assume 100 grams. You can turn the grams then of nitrogen into moles to compare it to the oxygen. Well done. Chemical formulas are mole ratios, all right? They're not like, this N2O doesn't mean 2 grams of nitrogen for every 1 gram of oxygen. It means 2 moles of nitrogen for every 1 mole of oxygen. So when you have a formula and you want to find it, you've got to figure out the moles related. What I would recommend is assume 100 grams total. You'd have then 46.67 grams of nitrogen, and you'd have 100 minus 46.67 grams of oxygen. Now, once you have the grams of nitrogen, divide by the molar mass. Nitrogen, the other number that is probably more useful than the atomic number. These numbers right here are molar mass numbers. They have different things. Nitrogen's about 14.01, and oxygen's about 16. Then you'll have those two mole numbers you can compare. Smaller one usually goes on the bottom, bigger one on the top. But in this case, you should find that those two numbers are almost the same, all right? So when I did it, I had 3.333 to 3.331, and that's almost exactly 1 to 1, which means the empirical formula here is nitrogen monoxide, or it's NO compound. So remember that formulas are mole-based. Percentages to grams, super common in chemistry. Assume 100 grams. You can assume any number you want, but 100's easiest. And then grams to moles using the molar mass. Questions on that? Okay. There's a video, by the way, for this whole review session. So if I say something too fast or later on, you're like, what did he say? I have a link to the video. I'll send it to you. All right. Here's a problem that looks kind of chill, but if you remember from Chem 221, if you see two reactant amounts, there's something special about this. So anyway, here's a question. We got 10 moles of N2, 25 moles of hydrogen. How much ammonia will we be able to produce? And again, there's a little bit of a trick to that. So you might want to check both reactants to see how much ammonia is made. So let's pretend that L is my boss. And L says, Russell, we got 10 moles into 25 moles of H2. How much ammonia are we going to be able to make? And I'm like, yeah, no problem. So the power of the balanced reaction is it's a ratio between reactants to products, as well as products to reactants and reactants to reactants, stuff like that. So I take the 10 moles, 1 mole of N2 needs 2 moles of NH3. So that means, if you look at this number, 20 moles of NH3. And I say, hey, yeah, 20 moles of NH3. And she's like, score. And she starts making all these calculations for money and things I don't understand because I work at a community college. However, Allie, since I see her, says, oh, I better double check Russell because he gets kind of caffeinated sometimes. So she looks at the other reactant, which is what you should do too, okay? And even though this number is a lot bigger than this number, the ratio over here is different, all right? So if you take the hydrogen, instead of 1 to 2 like it was for N2, you want to go 3 to 2 because there's 3 H2s for 2 ammonias. So to calculate the amount of ammonia made from hydrogen, you'll multiply it by 2/3, and up here it's by 2/1. And if you do that, lo and behold, it's less than the number I calculated earlier, all right? You're only going to be able to get 16.7 moles of ammonia here, all right? So L should fire me because I didn't check the other reactant. This is a limiting reactant question, all right? And it doesn't say anything about limiting reactant, but you as the hip chemist know it because you have two reactant amounts. Sometimes they're grams and you gotta go to moles first and then do these kind of conversions. Sometimes like this problem, they're moles directly. But we can only make, as scientists, 16.7 moles NH3 maximum. That's the theoretical yield, all right? This is falsely high, all right? This means that this is the limiting reactant, the hydrogen. This is the theoretical yield. It's the maximum amount of ammonia that can be made. And nitrogen, as it turns out, is the excess reactant. You're going to have extra of that hanging around. Cool. So really important in chemistry, you want to make sure you report the right amount that can actually be made and not some kind of artificially high value. Questions? Which of these compounds would be the best conductor of electricity in aqueous solution? What is the solvent if it's aqueous? Water, okay? So think about your knowledge from not only Chem 221, but also Chem 223 now. Which of those would be the best conductor? So up here on the chalkboard, I've written all but one. But what have I written up here on the chalkboard? What is this? Strong acids and strong bases. There's a lot of utility to these strong acids and strong bases, all right? In this class, Chem 223, of course, we saw that they always use the single arrow. We've seen that their conjugates, for example, sodium, potassium, lithium, as well as nitrate, perchlorate, etc., they don't affect pH because they're so strong, they don't do anything. But another use of this is that these dissociate 100%. So in solution, you don't have any HCl. It's 100% H plus and Cl minus. And you don't have any lithium hydroxide in water. You have lithium ions and hydroxide ions. And that's what it means to conduct something. You have to have ions running around. Now, if you look at these other systems up here, acetic acid, phosphoric acid, ammonia, and HIO, those are weak acids and weak bases. But HBr, I hope, is something you remember, because it's the last acid that wasn't listed. So these are super strong electrolytes. They dissociate 100%, and that means they conduct electricity. They're super strong acids and bases, totally product favorites, single arrows, no reason for double ones. They're conjugates, don't affect pH, so they just kind of sit there, which can be nice if you want something neutral. Any questions? Now, one of the questions on the some of the questions actually on the QA1 and QA3 were about net ionic reactions, net ionic equations. And what I'd like you to do in this problem is write what is the balanced net ionic equation for potassium hydroxide and iron 3 chloride. And this is an exchange reaction, so you could figure this out, but I'll tell you right now, you're going to get iron 3 hydroxide and potassium chloride. So see if you can use all that information or iron 2 hydroxide. So see if you can use all that information to find what the net ionic equation will be. One person's already got it. Boss. One thing I would focus on before the midterm, or the final, is if you're feeling uncertain about naming, that can be important. All right, and we're not going to get into super exotic examples, but if you are having problems knowing what these chemicals are, that would be something that try focus on, because if you can figure out the chemicals, then you can start figuring out like what's happening. All right, but if you're good to go, that's cool too. So potassium hydroxide. Potassium is a group 1A metal, and all of those +1 all the time. And hydroxide, which we've seen so much in Chem 223, hydroxide is OH -1. So KOH would be potassium hydroxide. Now the Roman numeral talks about the charge on the metal, so that's an iron +2. Chloride is in group 7A on the far right. All of those 7 - 8 -1 will be their charge. So because iron's +2, chloride is -1, you're going to need 2 Cl- to balance the iron. So this is iron to chloride. And then the other side, same kind of thing. This is still iron +2, hydroxide's -1, so you'll need 2 of them. Notice the parentheses around polyatomics. There's no parentheses when it's just one atom. And then potassium chloride is a K+ and a Cl-. Questions on that part? Okay, now the newer edition, which we've talked about briefly in Chem 221, and now this quarter, is talking about the states of matter and how to find them out. And of course, if you have a KSP, that's almost always means it's going to be solid. But another thing you can do is remember that all of these up here are super good at dissociating, KOH, NaOH, stuff like that. So this one will be aqueous. It's a strong base. All right, all of these up here you would put AQ next to, absolutely. Now, 2 of these species have chlorides, and in the group 1A cations lab we did chloride, bromide, and iodide, usually AQ, unless they're with lead, silver, and mercury. And why that's important, iron is not lead, silver, or mercury, so you'd say AQ. And potassium is not one of those either, so you'd say AQ, all right? Anything with potassium, sodium will always be AQ, but that's another kind of way to figure it out. And then finally, most hydroxides that aren't sodium, potassium, lithium are going to be insoluble. So you put an S next to it. So this reaction right here is the balanced molecular reaction. And what it's saying is that you've got two solutions, you're adding them together, you will see a precipitate, which is iron 2 hydroxide. Questions up to there? So let's say we get excited and we're like, oh, let's do this. Let's make some iron 2 hydroxide. It's kind of a weird brownish red color. It's kind of cool. Not that cool, but kind of cool. So we get excited. We're going to lab. We're going to do this. And oh, man, lab's out of potassium hydroxide. So we all go home with sad faces. No, wait a second. Because if you understand what a net ionic equation is, a lot of times you can substitute, all right? In this reaction, everything that's AQ gets broken up, but don't break up solids, liquids, and gases. So the FeOH2 stays the same, but this you break up into K plus and OH minus. And this you break up into Fe2 plus and Cl minus. And if you look over here, this is also broken up into K plus and Cl minus. K plus is on both sides, all right? It's part of an aqueous thing. So what that means here is that the potassium is a spectator ion. It doesn't participate in the chemistry. The hydroxide is needed to make the insoluble FeOH2. So you can absolutely substitute for potassium hydroxide, sodium hydroxide, or lithium hydroxide. And turn those browns upside down. You all of a sudden then, woohoo, we get to make the FeOH2. So spectator ions are cool because if you don't have a chemical, a lot of times you can substitute the active part and still make the stuff happen. In this reaction, the chloride is in an aqueous part on both sides. Chloride is the spectator, and so is the potassium, because potassium's there. So you only write what's left at the net ionic part, and that is going to be answer C right there. So that's why it's cool, all right? Because inevitably, the best laid plans, you don't have some chemical when you're ready to rock and roll with it. If you know about this, a lot of times you can make substitutions and still have the same results. Any questions on that? Another kind of question that we dealt with this term and Chem 222 and Chem 221 is on molarity, all right, making solutions. Now, big M is not moles, big M is moles per liter, and it's by far the most common unit of concentration. So in this problem, we're taking this many grams of sodium carbonate and we're dissolving it in 250 milliliters of solution. And here's even the molar mass of sodium carbonate. See if you can use that information to find the concentration, the molarity of the sodium carbonate. Outstanding. How many milliliters in a liter? 1,000. Good. That'll be something you'll do next Wednesday. All right, so just make sure you know that. So 250 milliliters, you have to turn into liters. You'll divide it by 1,000. That's basically like moving the decimal to the left 3 points if you want. Grams divided by grams per mole give you moles. And then finally, moles divided by liters will give you the molarity. And if you did all that, you should get 0.254 molar. Molarity is different than molality, which we'll talk about later. Any questions on that? Cool. We have time for one more question. This is an oxidation number question. It says, what's the oxidation number of the manganese in KMnO4? Oxidation number is like the charge, all right? Remember the oxygen's usually -2. See if you can figure that out. So you're smarter than me. If this problem totally bums you out, here's another way to think about it. The whole molecule doesn't have a charge, it's 0. So you can say that all the oxidation numbers, so the oxidation number of potassium plus the oxidation number of manganese and 4 times the oxidation number of oxygen, all of that equals 0, all right? So almost always oxygen is -2. That's almost like standard. There's a few exceptions, but that's very, very common. And what is potassium equal to? Almost +1, good, that's right. So really, the only one you don't know here is the transition metals because they're variable charge. Nobody knows for sure. But you can see it's like 1 plus x minus 8 equals 0. That's like one way to solve it. And if you do that, oxygen comes out to, or the manganese comes out to be positive. So, any questions?
How do you find the highest reverse oxidation for like the transition?
The B groups work for a lot of them. So manganese is 8 because it's in group 8B. That's right. It usually doesn't want to go to the 3p electrons. So 1, 2, 3, 4, 5, 6, 7 goes backwards. Then it's left. Oh, it's a 7. Sorry, not an 8. But yeah, I wasn't reading my book. That's fine. But usually doesn't.
Just the number of.
That's right. Cool. All right, we'll do some more on this on Friday. See some more presentations on Friday. Should be cool. Have a great day. Oh, make sure you turn in the assignments up there if you haven't done it. I think everybody has a, yeah. Have a good day.